In this video, we're going to look at like 10 different examples of using the chain rule or the general power rule. And I encourage you in this video to pause each example and try to go through it before you watch me going through it, especially after you get the hang of it, after watching maybe one example. Doing mathematics is really the only way that you can get good at it. Watching someone else do mathematics doesn't really work. So let's get started with example number 1. Remember before we started, I guess, that we have our general power rule, which allows us to find the derivative of functions that are that look like some kind of function of x raised to a power. Before we have this simple power rule, that's just x, the single variable raised to a power. They're related in that when you differentiate something like a function of x raised to a power, you differentiate the outside by using what looks like the simple power rule, leaving the inside function the same, and then we multiply by the derivative of the inside. And I'm using b here again for base because it's what is raised to the power. So the key thing in using the general power rule is recognizing what is the base. The power is generally pretty straightforward. And when you can recognize the base and find its derivative, then you're pretty much good to go with using the general power rule. So in example 1, we've got y equals 3x minus 2x squared, all raised to the 4th power. So the base here, right, is going to be, of course, 3x minus 2x squared. So what we have here, just to kind of simplify the way we're looking at this, we've got like b to the 4th. So we need to find now the derivative of the inside. That'll be 3 minus 4x. Now it's just using our simple rules. So notice how these are all building on each other. You might need to review the simple power rule and other rules before you start building on it with the chain rule. If that's the case, feel free to go back to previous sections. So the way we would differentiate, here's how I would think about this. The way you would differentiate b to the 4th, well, you'll bring the 4 down and multiply, subtract 1 from the power. But then because b actually represents something more than x, we have to multiply this by the derivative of b, the inside. So when we use this to differentiate the whole thing, the whole function y prime, we bring the 4 down and multiply in front of the whole thing. We subtract 1 from the power, so we get 4 times 3x minus 2x squared, all raised to the 3rd. Okay, so here's the 4b cubed. And then we have to multiply this whole thing by the derivative of b, by the derivative of the inside. And that we found over here was 3 minus 4x. So here is the b prime part. Now in terms of simplifying derivatives that are found by using the chain rule or the general power rule, really the only thing that you can often do to simplify is multiply the power that came from this part, the 4 here in this case, the power that we bring down and multiply, and the derivative part of the inside. If it's a number, if this were just like 3, then it would be best to multiply these together. But here, this is all nice and factored. And factored form is always the best form that you could possibly have. So I would say that this is pretty simplified and we don't really need to do anything else here. So here's the derivative. In example 2, we've got y equals negative 4x cubed plus 10x squared minus 3x plus 2. And that is all raised to the 7th power. So here what we have is some stuff to the 7th. So we want to just kind of look at the structure of this and think, okay, like I've got some stuff to the 7th. Let's just simplify that in our minds and we'll call this b to the 7th, right? Where of course b is the stuff that's raised to the power, but not including the power. So we're going to use the general power rule here, and so we'll need the derivative of the inside. We'll need b prime. That'll end up being negative 12x squared plus 20x minus 3. Okay, so then we think about b to the 7th. Using the general power rule on that's derivative will become 7b to the 6th times the derivative of b, or times b prime. So that means we put it all together, y prime, or the derivative of the whole function. Okay, we've got 7b to the 6th. So really what we're doing is we're bringing the 7 down and multiplying it by the whole thing here, what we were calling b. And then we subtract 1 from the power, so that now gets raised to the 6th power. Okay, so here is the 7b to the 6th. Then we multiply all of this by b prime. Of course, that is this derivative of the inside, which we found right here. So this is times negative 12x squared plus 20x minus 3. Here is b prime. Now again, in terms of simplifying these kinds of derivatives that are found by the general power rule, this part here that is kind of base to the 1 less power, if that's not squared, or to the first, I guess, then you don't really want to like expand all this out ever. You can't just distribute powers over plus and minus. So generally that is going to stay the same. Again, what you might look at simplifying is the number that's in the front here and the derivative of the inside. It wouldn't necessarily be simpler to distribute the 7 into here. You definitely cannot distribute the 7 into here and here and here and here. So again, this is probably simplified as far as we'll look at it. So there's y prime. Okay, in example 3, we've got f of x equals 4 times 5x to the 4th plus 1 raised to the 100th power. Now here we have a 4 in the front of some stuff to a power. We have to remember all of our other rules from before. So this 4 in the front of the entire, the stuff we've got to the 100th power, this is a constant multiple. So when we find the derivative of the part that's the variable part that's multiplied by that 4 here, we can just multiply that by the 4, and that will be the derivative of the whole thing. Remember the constant multiple rule, the constant just stays and multiplies by the derivative of whatever variable stuff that it's multiplied by in the original function. So what we have here, this whole thing, right, we've got 4 times some stuff to the 100th power. So if you want, we can look at this as 4b to the 100th. Right, where of course b is 5x to the 4th plus 1. And then b prime will be the derivative of that, which is 20x to the 3rd. So if we're going to think about differentiating something that looks like 4b to the 100th, that 4 will just multiply by the 100 when we bring it down, just like when the b is just x, right? 4x to the 100th, you would bring that 100 down and multiply by the 4. So this will differentiate into 400 b to the 99th. And we have to multiply that by b prime. Okay, so the derivative of f of x now will be f prime of x. So it'll be 400 b, which was 5x to the 4th. So the base again stays the same. We subtract 1 from the power. Oh, iPad. Okay, there we go. Okay, so the 100 comes down, multiplies to give us 400 here. The base stays the same. We subtract 1 from the power to get 99. And then we have to multiply this by the derivative of the inside. And that was 20x to the 3rd. Okay, so again, just here we've got 400b to the 99th. And then here is b prime. Now, if you can see this and you don't want to use the b and have all this kind of work on the side, that's no problem. If the b helps you to kind of piece out, the different pieces and simplify things, then I hope that this structure is helpful for you. In terms of multiplying or simplifying this, here we have a kind of like a monomial, a single term as our b prime. So it wouldn't be a bad idea to just take the 400 and multiply it by the 20x to the third, and just put that in the front. So 400 times 20 is 8,000. We'll bring the x cubed out in the front as well. It's just kind of standard to put single things like, this would be a thing with a single term out in the front, and then anything else that's a little more complicated back in the end when you're multiplying everything together, but not a big deal if we wanted to leave it as it was before. So there's f prime. Okay. Just as before, when we wanted to differentiate something with the square root, we also have to kind of rewrite this as something to a power instead of a radical. So remember that the square root is the same as raising to the 1/2 power. So we first want to rewrite this function, which is f of t equals the square root of 2t squared plus 3, as parentheses 2t squared plus 3, all raised to the 1/2 power. Now this looks like something that we were just differentiating before. So just recall that when you have square roots, you still have to rewrite this as a power in order to use the general power rule. All right, so let's see, we've got here we've got some stuff to the 1/2. So we'll say that that's b to the 1/2 power, where of course the b is 2t squared plus 3. Now I know I'm going to need b prime, so I'll just find that derivative here. That'll be 4t. Okay, now differentiating some stuff to the 1/2, that looks like 1/2 b to the negative 1/2. And then because b is more than just x, or a variable to the first power, we have to multiply that by the derivative of the inside, or by b prime. So putting that all together, we will find f prime of t. So you can follow this formula, or if you want to get used to more visually seeing what's happening, we'll bring the 1/2 down in the front of everything and multiply. We leave the inside the same, the base, the inside, and then we subtract 1 from the power, so it'll be negative 1/2. Then we have to multiply, going in one step to the baby, or right, this is the mother that we differentiated, and now the baby is the base. We have to differentiate that. Right, we found that the derivative of that is 4t, so this will all be multiplied by 4t. Now simplifying this, we probably want to get rid of the negative power. So let's see what we have. Well, that's one thing we want to do. I might suggest, so here we have a monomial, or a single term. Here we have a number. Again, when that's the case, it's nice to combine these things together by multiplying them and maybe combining the numbers together if you can. So the 1/2 and the 4 can multiply to give us 2. So we've really got this stuff to the negative 1/2 raised to the 2t, times 2t. So if we're going to rewrite this without a negative exponent, the stuff that's raised to the negative power, the 2t squared plus 3 to the negative 1/2, all that stuff can go down to the denominator. And instead of negative 1/2, it'll have a positive 1/2 power. The 2t that's left over here does not have a negative exponent on it, so that will stay up top. So we've got 2t over 2t squared plus 3 to the 1/2 power. If you want, you could rewrite this as a radical. So it'll be 2t over 2t squared plus 3 square root. And there is f prime of t. Okay, in example number 5, we've got y equals 2 over x squared plus 1. Now this is a quotient, right? I mean, we've got a function that has a numerator and a denominator. Why is this in the general power rule section? Well, the quotient rule, if you recall, is only necessary when you have some variable stuff in the numerator and some variable stuff in the denominator. Here, we only have a variable part in the denominator, but in the numerator, there's just a constant. There's just a number. There's no x's up top. So when that's the case, it's not wrong to use the quotient rule, but I think you'd agree that the quotient rule is complicated, right? It's more complicated than the general power rule. It's probably our most complicated derivative rule. So when you have something that has this form where you have a number over variable stuff, here's like a pro tip from me to you that you probably want to consider rewriting this. And I'll show you how. Rewrite to use the chain rule or the general power rule instead of the quotient rule. Now, if you love the quotient rule, like I said, it is not wrong to use the quotient rule on this, but there's many more like areas for some kind of small mistake. So I don't know, I think there's fewer steps to use the general power rule, and I really recommend that you take this route whenever you have a function that has this structure. So the way that we would rewrite this is we would look at the denominator, the x squared plus 1, and think of that whole thing being raised to the first power underneath. So because 2 is divided by all of x squared plus 1 to the first, we can rewrite this as 2 times x squared plus 1, not to the first, but to the -1 power. And now we can see that this has the format of something that we can use the general power rule on. I think this is really cool. It's, it's much simpler, again, in my opinion, than using the quotient rule. You'll encounter a lot fewer algebra steps to simplify if you just take this little step to rewrite instead. So let's see what we've got. We've got a 2 in the front. That's okay, right? That's no problem. That's just a constant multiple. Then we've got some stuff raised to the -1 power. So what this thing looks like is 2b to the -1. That is pretty simple to differentiate using our general power rule. So just to be clear, our base here, right, is x squared plus 1. We're going to need b prime. That is, of course, 2x. So then we think, how do we differentiate 2b to the -1? Well, that's going to look like bringing the -1 down and multiplying by the 2. So that's -2b. We subtract 1 from the power. Be careful, that puts us more negative at -2. -1 minus 1 is -2. And then we'll have to multiply by the derivative of the inside, times b prime. Okay, so let's piece this together. We've got the derivative of the entire function now. So we'll call that y prime. Okay, now we're thinking about this way of writing this. So the -2 comes down and multiplies by the 2. That's where this -2 comes from, right? So we have -2. We keep the base the same. We subtract 1 from the power. And then this gets multiplied by the derivative of the inside, which we found was 2x. Okay, so again, here what we have here is -2b to the -2. And then here is b prime. Now to simplify this, what we should do is just look at, again, the number here and the derivative of the inside and see if it makes sense to combine those together by multiplying. So I think in this case it does. Negative 2 times 2x is negative 4x. Now we also have this negative exponent here, which would be simpler if we rewrote this as a fraction. So this multiplication times the negative 4x can change into division if we make the exponent a positive 2 instead of a negative 2. So to last step here to simplify, the negative 4x will stay up top, and the x squared plus 1 can go down in the denominator, and we'll end up making its exponent positive. So there's the derivative of this function. Okay, example number 6. This one is very similar to the previous example, so I'd encourage you, if you haven't been doing this already, to pause this video and try this question on your own. So again, here what we have is a number up top and variable stuff in the bottom. So I would recommend to rewrite this to, again, avoid the quotient rule. The chain rule is easier. So the way that we would write this would say, all right, well, this whole stuff in the bottom can come up and multiply by the negative 3 if we just make its exponent, this 2 here, a negative. So that'll look like negative 3 times 1 minus 4x squared, all raised to the negative 2 power. Okay, so then thinking about what we have here, what this looks like, it looks like we have negative 3 times some stuff b to the negative 2. So to differentiate this, that'll look like bringing the negative 2 down and multiplying, so that's positive 6. We leave the base the same. We subtract 1 from the power. That'll put us at negative 3. And then we multiply by the derivative of the base. Okay, so and just to be clear, here is what b is. Here's the base. It's the inside stuff, the 1 minus 4x squared. And the derivative of the base is negative 8x. All right, piecing this all together into our derivative of the entire function, g prime of x. Let's see, so again, if you like using the b here and plugging into the formula, by all means go ahead. Try to train your eye though on eventually and just kind of see how it fits together if you can. So right, this negative 2 comes down and multiplies by the negative 3, so that gives us positive 6. We leave the base the same, the 1 minus 4x squared. Then we subtract 1 from the power, so that's negative 3. Okay, so here is where we have the 6b to the negative 3. Then we multiply this by, we go inside, that's the mother derivative, we differentiate the inside, the baby now. And so the derivative of 1 minus 4x squared is negative 8x. So this will all be multiplied by negative 8x. So here's b prime. And now pause this and try to simplify this. So again, we have a 6 in the front times a single term as from our b prime. So we want to combine those together by multiplying them. So 6 times negative 8 is negative 48. And then lastly, we can change this into a fraction. We have multiply here by the negative 48x. So this will change to divide if we just make this exponent a positive 3. So the last thing to do is write this as a fraction. Negative 48x divided by 1 minus 4x squared, all raised to the positive 3 power. And there is g prime of x. Okay, example number 7. We've got y equals 8 over the square root of 3x squared plus 4. Now again, we have a constant up top or a number up top. So whenever you see a fraction when you're differentiating, just check and see what kind of fraction it is. Is it a number over variable stuff? Or is it variable stuff over variable stuff? Or is it variable stuff over a number? Because in each one of those cases, you'll do something a little bit different. So in this case, we've got a number over variable stuff. So we want to rewrite to use the chain rule. So pause this and rewrite this as a general power rule situation, and check back in with me when you're done. Two things here. First, we want to maybe get rid of that radical. Write that as 1/2 power. Then we want to bring this up. So we'll write this as 8 times 3x squared plus 4, all raised to the negative 1/2 power. Okay, good. This is now a number times some stuff to a power. That's a great thing to have to take the derivative of. So let's see, we've got this 8 here. This is a constant multiple. All right, then we have this whole thing looks like 8 times some stuff, b to the negative 1/2 power, where of course b is 3x squared plus 4. We're going to need the derivative of that, b prime, and that is 6x to the first. All right, so we look and see how we're going to differentiate 8b to the negative 1/2. Well, we'll bring that negative 1/2 down and multiply by the 8. So that's negative 4b. We'll subtract 1 from the power. Negative 1/2 minus 1 is negative 3/2. Then we have to multiply this by the derivative of the inside, by b prime. All right, now we're all set to take the derivative of the entire function here. Again, looking at it in this form. So y prime is going to be, either look at this and plug things into your formula, or if you don't like that, just try to train your eye to see, okay, the negative 1/2 is going to come down and multiply by the 8. That's negative 4. We leave the inside the same and subtract 1 from the power. Then we have to go inside and differentiate the inner function, the 3x squared plus 4, and multiply this whole thing by its derivative, which is 6x. So again, here we've got negative 4b to the negative 3/2, and then here we've got b prime. Now simplifying this, it's going to follow the same format that we've been doing, where we'll look and see, okay, is b prime a single term? If so, we probably want to combine it with the number that's out in the front. So negative 24 times 6x, whoop, my brain got ahead of me there. Negative 4 times 6x is negative 24 x. Then we've got 3x squared plus 4 to the negative 3/2. And then lastly, get rid of that negative power. We've got negative 24x. All of that is multiplied by that stuff to the negative exponent. So this will change to a divide if we just make this exponent positive 3/2. So we've got negative 24x over 3x squared plus 4 to the positive 3/2 power. There is y prime. Okay, so what we looked at so far is differentiating some stuff to a power by itself. Maybe we've looked at when you have a constant multiple in the front. Then in these last 3 examples, 5, 6, and 7, we saw that we can sometimes rewrite a fraction to use the general power rule instead of the quotient rule. I'd like to take a little bit to show you how this combines with our other differentiation rules. So sometimes we have functions that need the quotient rule and the product rule maybe, along with the chain rule to be differentiated. So what does that look like? Let's look at example number 8. So this is x cubed times 2x minus 3 whole thing squared. So now what we have here Our outermost function, or our outermost operation, like globally, the bigger picture of this function is that we have something, x cubed, times something else, 2x minus 3 squared, and both of those things that are being multiplied have variables in them. When that is the case, 100% of the time, you will need the product rule. Okay, maybe not 100, but unless you can, get rid of the product somehow, like we could expand this out by FOILing and then distributing the x cubed. But when you can't do that, or you don't want to do that, then you have to use the product rule. Excuse me. Now, within the product rule, we're going to need to differentiate each part. X cubed is easy. 2x minus 3 to the second, that's going to need the chain rule to find the derivative of. So let's just start with what we have first. So this is going to need the product rule. So flip back in your notes, or I'll share with you, I'll remind you what the product rule says. So one way that we can write it is u times v derivative is u times v prime plus v times u prime. First times the derivative of the second plus second times the derivative of the first. I always say that in my head when I'm finding the derivative using the product rule. I think the words are more helpful than the symbols, but whatever makes it easy for you. So let's parse out what u and v are. So let's see. We've got, let's call this u. And let's call this one v. Okay, now we need to find the derivative of each of these pieces to use the product rule. Okay, so u prime, that's 3x squared. Now v prime, and here's where we need the chain rule. Now, I don't know if having another letter here is going to be more or less confusing. So if you want, you could say, all right, well, we need like b is going to be the 2x minus 3. Then we'll differentiate that using the general power rule formula with the b. And I think it might be good to use that and then try to wean yourself off of it at some point. But anyway, here, if you need it, if this is just extra confusing, don't worry about it. So the base here is 2x minus 3, right? And then, of course, we have b prime, that'll be 2. So to differentiate our v, we're going to bring the 2 down and multiply. We leave the inside the same. So it'll be 2 times 2x minus 3 to the first power. Then we have to multiply all this by b prime. So it'll be times another 2. Okay, so again, here's 2b to the first, and then here's b prime. And that's how we would differentiate b to the second. And you might need to pause this and rewind and go through it again. That's okay. That's actually why online classes can be good, because you can pause stuff and rewind when things get a little complicated. Or maybe you need to go take a break, and that's okay too. So anyway, now that we have our pieces, we can put this together into the product rule. Now I like to make these x's here, and everything that's connected by a line, these two and these two, get multiplied together. And then we add the results. So to differentiate the entire function, we've got u, which is x cubed. Then we've got times v prime. Now, before we go actually into the product rule, I might just simplify the v prime here. Again, by leaving this alone, but taking the result of b prime and the number in the front and multiplying those. So I might just write this as 4 times 2x minus 3. Just gets rid of some parentheses. So what we'll have here is x cubed times 4 times 2x minus 3. Then we add v times u prime. So these two are what we're going to multiply together. Now, it doesn't matter which order that we multiply these in. I'm just going to write the 3x squared first and this stuff second, because we normally write like a single term piece in the beginning and then a multiple term piece in the end. So we've got 3x squared times 2x minus 3 all raised to the second power. So here's the end of the calculus part. Sorry, I just had to sneeze, but it went away like right when it was gonna come out. I hate that. So here's the end of the calculus part of this question. Now, to simplify this, it is a little bit different than before, right? Because we have basically two different pieces here, separated by a plus. The way to simplify something like that is generally by factoring. So I would recommend first rewriting this in a way where you don't have so many parentheses, because it's really hard to see what's happening. So we're going to look at this in like two chunks here. We've got this chunk and this chunk. Now in the first chunk, and just to be clear here, what we're doing is simplifying. The x cubed times 4 times 2x minus 3, that'd be better if we just wrote that as 4x cubed times 2x minus 3. Then also we don't need the parentheses in the second chunk around the 3x squared. We can just write that as 3x squared times parentheses 2x minus 3 squared. Okay, now what we're looking for, again to simplify, is the greatest common factor that we could take out. So simplifying this will not mean distribute here, FOIL and distribute here. Generally with derivatives, we want to factor them. And the reason for that is going to be clear in the next chapter when we're going to use the derivative to tell us a little more things about, like situations. And if we have a factor derivative, that will be easier for us to use. So why not practice now? So the GCF that we're looking for is going to be found by looking at each part individually. So we're going to look at, again, each chunk here. So we look at the number parts, 4 and 3. No common factor that can come out of those. We've got x cubed and x squared. There is a common factor of x squared that could be pulled out. Then we look at 2x minus 3 and 2x minus 3 squared. There's a 2x minus 3 that we could pull out of each of the chunks. Okay, so here is the GCF. Now to figure out what's left over, again, from each of the green pieces here, if we take out, well, we didn't take out a 4, right? So that's going to be what's left over, at least here. We took out x squared from the x cubed, so it'll be a x to the first left over. And we took out 2x minus 3 to the first. So there's no more 2x minus 3 in the in our first green chunk after we factor out the GCF. Then we have plus. Okay, the plus that's separating the green pieces. So we didn't take out a number, so there's still going to be a 3 in that part. We factored out the x squared, but we only factored out one of the 2x minus 3's. So that 3 is going to be multiplied by 2x minus 3. Okay, now we want to simplify what's left over after we took out the GCF. We already factored out everything that could be factored. So now the way to simplify this would be to expand and collect any like terms. I know simplify can mean different things in different contexts. It's hard to know when to use what. But just thinking ahead, right, if we distribute this 3 into here and here, we'll have some x's that we can combine with the 4x. And that would be simpler. So we're going to leave the GCF alone. We'll distribute the 3 into the parentheses. And then lastly, we'll just combine those x terms together. The 4x plus 6x. That'll give us 10x and then minus 9. And I don't know, that's a pretty neat derivative, like when it's all fully factored like that. It's definitely it's easier on the eyes. It's just a neat little package. And like I said, we will kind of need to do this soon, so why not practice now? Okay, example number 9. And I've only got 10, so we're almost there. Example number 9, we've got a function h of x equals 2x times the square root of 1 minus x squared. Now, if you don't know where to start, generally when you're finding the derivative of something, radicals or roots are probably not a good place to be, especially for differentiating. So at the very least, the first thing I would say is let's rewrite this with a 1/2 power instead of a root. Now, looking at this, what we have is bigger picture-wise, we have some stuff with x, 2x, times some other stuff with x, 1 minus x squared to the 1/2. Variable stuff times variable stuff. No way to get out of the fact that there's a product here. So this, again, is going to need the product rule. So again, here's the product rule. The derivative of u times v is the first times the derivative of the second, plus the second times the derivative of the first. So what we have for u and v, let's see, so the first one, u, I would say, is 2x. Then v, of course, will be 1 minus x squared to the 1/2. All right, we need the derivative of each of these. So u prime, the derivative of 2x will be 2. And v prime, here is where we need the chain rule. Right, so chain rule. Right, what we have here is some stuff to the 1/2. So b to the 1/2. So b is 1 minus x squared, and b prime, that's negative 2x. So when we differentiate b to the 1/2, that'll give us 1/2 b to the negative 1/2 multiplied by b prime. Okay, so we'll get 1/2 down in the front, b base stays the same, subtract 1 from the power. And this all gets multiplied by b prime, so it'll be multiplied by negative 2x. All right, now, and this we're done with the chain rule part, but we do need to put this together into the product rule to find the derivative of the whole function. To simplify this, I would recommend doing that first. We have a number here, 1/2, and a negative 2x here. Right? These are the parts that we want to see if we can multiply together. The 1/2 and the negative 2, those are going to cancel, and we'll have negative 1. And so this can be rewritten as, I'm going to bring the negative x in the front, and then we've got 1 minus x squared to the negative 1/2. Now, we would like to eventually write this as a fraction without a negative power, but I would recommend that you do that in the very end, and you'll see why when we put this together into the product rule. All right, so h prime of x, the derivative of the entire function. Okay, it's first times the derivative of the second, so it's 2x times the derivative of the second. That's negative x, 1 minus x squared to the negative 1/2. And I think that's it, right? So here, so it's u times v prime. Then we're going to add v times u prime. So we add v, the second, 1 minus x squared to the 1/2, times the derivative of the first. So it'll be multiplied by 2. Now again, here's the end of our calculus. Now we just have to simplify this using algebra. So simplify. Now I would first recommend that you get rid of all of the parentheses and rewrite things with like single terms in the front and then more than single term, like a 2-term thing or something after that. So in other words, in this first, let's make this a green blob. So we'll always have 2 green blobs when we're doing the product rule. In the first green blob, we have 2x basically times negative x and then times all of this stuff. So, there's associative rule in math. We can multiply these two things together, change their order around. So 2 times negative 1 is negative 2, and x times x is x squared. And then we'll just leave that 1 minus x squared to the negative 1/2. Then the 2 at the end there is normally rewritten in the front. If you could see my video behind me, you would have just seen my cat dart down the hall for unknown reasons. Now he's just standing still in one spot. Now this looks better, okay? Easier to maybe factor. So again, that's the way we want to go after we kind of get rid of all of the parentheses. So GCF. Okay, so you look at the numbers. We've got -2 and +2. Okay, so we could take out a, well, either way you want to think about it. I'll just say, how about a +2? You could take out a -2 if you want. Then we have x squared. There's no x's by themselves here, so we can't do anything with that. Then we have 1 minus x squared, 1 minus x squared to different powers. When you take out the GCF, you can only take out the smallest power. You can only take out the smallest power that appears. So the smallest power here is negative 1/2. So we're going to take out a 1 minus x squared to the negative 1/2 power. And here's the GCF. All right, so what we have left over, well, we took out a 2, so there's going to be a -1 left. We're still going to have x squared. And we factored out that 1 minus x squared to the negative 1/2. Okay, then we'll add. We factored out a 2. Now we have to figure out what's left over here. So when we factor out something, we are basically dividing by it. So when you divide something, like for example, if you factored out, let's say we've got x to the 5th plus x cubed. If we factored out an x cubed, we would get x squared plus 1. So you're dividing this x to the 5th by x cubed, and you get x squared left. And then, of course, this doesn't go away. It stays out in the front as the GCF. So when we factor out the 1 minus x squared to the negative 1/2 from 1 minus x squared to the positive 1/2, we will end up subtracting the power of negative 1/2 from 1/2 because we're dividing something that has the same base. Just like we would subtract the 3 from the 5 to get a 2 left over. So 1/2 minus negative 1/2 is going to end up being 1/2 plus 1/2, which is to the first. Okay, so now that we have that factored out, we want to see if we can simplify this. Simplify what's left over after you take out the GCF. We've got negative x squared plus 1 minus x squared, so that's negative 2x squared plus 1. Okay, then the last thing to do is get rid of that negative power right here. So this is being multiplied by the 2 and the negative 2x squared plus 1. So the 2 and the negative 2x squared plus 1 are going to stay up top in the numerator and be multiplied together. But the 1 minus x squared can be moved down into the denominator, and its exponent can become positive. So I'll say 2 parentheses, negative 2x squared plus 1 divided by 1 minus x squared to the positive 1/2. Or if you want to rewrite that as a radical, that's totally fine too. And there is the derivative of that function that we started with. This is hard stuff. Definitely so many steps. Practice, practice, practice makes perfect. So, do some practice problems to get better if it's a little bit difficult right now. I know you can get good at this if you do some practice problems. So I'd like to share one more example with you, example number 10. And that is y equals x over 3x minus 1 all raised to the fourth. Okay, so here we have a function raised to the fourth power. So the biggest outermost thing we have is some stuff to the fourth, right? That's like the main idea of the function, is it's raising something to the fourth. The something that we have is a quotient. So in the previous two questions, our big rule outside was the product rule, and inside of the product rule, we were using the chain rule. Here, we have some stuff to the fourth. That will need the chain rule. When we're finding the derivative of that stuff, here we've got a quotient with variables up top and variables down bottom, and that's going to need the quotient rule inside of the chain rule. So there are lots of ways you can combine these rules together. I can't do examples with all of those ways, but here is a different kind of way that these can be combined. So let's see. Right, overall what we have is b to the fourth, where b, the base, is x over 3x minus 1. So to differentiate b to the fourth, we're going to do 4b to the third times b prime. So we're going to need to find b prime. To do that, we are going to get to use the quotient rule. All right, so let's remember what the quotient rule says. Flip back in your notes and find it. So it says that if we want to differentiate something over something else, we get another fraction. It's bottom times derivative of the top minus top times derivative of the bottom, all over bottom squared. All right, so here's n, here's d. So n prime is 1 and d prime is 3. So when we put this together into the quotient rule, we will get bottom 3x minus 1 times the derivative of the top times 1 minus top, which is x, times the derivative of the bottom, which is 3. And that's all divided by the original denominator squared. Now, it's probably going to be really nice for us, future us, if we simplify this before trying to put it into the formula for the derivative of this whole thing. So 3x minus 1 times 1, that's just 3x minus 1. X times 3, that's just 3x. 3x minus 3x, that those cancel out, and we are just left with negative 1 over 3x minus 1 to the second. Okay, so I think we're ready to put this all together into the general power rule formula here. All right, so y prime. We bring the 4 down and multiply in the front, leaving the base the same and subtracting 1 from the power. So that'll be 4 times x over 3x minus 1 to the third. Okay, so here is 4b to the third. And then we have to multiply this by b prime, the derivative of the inside. So that's the thing we found using the quotient rule. So that's negative 1 over 3x minus 1 squared. So here is b prime. Oh, iPad's been doing so good today. Oh, here we go. Okay. Now, on first glance, this doesn't really look like something that we could simplify. And if you want to leave it like this, honestly, that's fine. But I look at this and I say, well, these denominators are like almost the same. except this one is trapped inside of this thing that's raised to the third, and it's this whole fraction. So one thing that we could do, and optionally, and it's a good review of all of our algebra rules, is to kind of split up this divide, this fraction, by raising the numerator to the third and the denominator to the third separately. So again, here is like encouraged but optional simplifying. So what I mean by that is we can write this as x to the third over 3x minus 1 to the third. And that's times negative 1 over 3x minus 1 to the second. Now we have basically 3 fractions multiplied. 4 is really 4 over 1. And when we're multiplying fractions, we can just multiply across the numerators and multiply across the denominators. When we multiply across the numerators, 4 times x cubed is 4x cubed, times negative 1 is negative 4x cubed. In the denominator, we've got 1 times 3x to the third times 3x minus 1 to the third times 3x minus 1 to the second. These have the same base, and we're multiplying them, so we can add their powers together. So this will just be 3x minus 1 to the 3 plus 2, which is to the fifth. And I don't know, that just seems like way better than the thing that we started with. And it only took, didn't take that long. So I would say here's our fully simplified derivative. So this is the end at the moment for our quotient rule practice. I've got one more little application to I think I just said quotient rule practice. It's not even Monday and I'm like already I'm already having trouble. I'm sorry about that. So this is the end of our chain rule practice. I've got one more little application that I will do in a short video coming up. And I will see you then.